All right, I guess we're going. So, Sumit is a PhD student in the University of Gdansk, working with Professor Pavel Horodecki. He's interested in the foundations of quantum mechanics, including non-locality and indefinite causal order, and exploring advantage of quantum resources in information theoretic tasks. Let us all welcome our speaker.
Hello, everyone, and good afternoon. I'm Sumit, and today I'm going to talk about our work on unbounded quantum advantage in one with strong communication complexity of relation. This is a task we introduce in our work, and for this task, we consider some special kind of relations based on distributed clique labeling problems. This work has been done with collaboration with Nitika Shekarwade, Somsankar Bhattacharya, Ravi Shankar Ramanathan, and Professor Paul Horodecki, who is also my PhD supervisor. So before I start my talk, I would sketch the outline first. Starting with communication complexity of relations, I will tell what the task we consider the strong communication complexity of relation in our work. Then I'll briefly talk about orthogonal representation of graph, binary clique coloring problem, and clique labels. Based on this, I will introduce the distributed clique labeling problem that we explicitly consider for communication complexity and strong communication complexity. In the first part of strong communication complexity of relations, I would be focusing on a scenario where no public coin assistance is allowed. And then I will talk a bit about the scenario when some public coin assistance is present between Alice and Bob. And later on, I will talk about some applications, following which I will draw some comparison between our work and pre-existing works that show exponential advantage, and conclude with some open questions. All right, let's start. In the case of communication complexity of relations, one considers in a bipartite scenario, three sets, X, Y, and B, and the Cartesian product of the set R is a subset of the Cartesian product of X, Y, and B. And here Alice receives an input from the set X, while Bob receives an input from set Y. And at the end, their objective is to specifically Bob to calculate B such that the triplet XYB belongs to some relation R. To do this, they may exchange message in one round or in multiple rounds, and the amount of message they exchange is say M in amount. And this scenario has been fairly considered in many works before. And while doing such tasks, they may have assistance of private coins, which is the local source of randomness. And some of the works allow for public coins, which is the shared correlations between Alice and Bob. And the system in which they choose to do their encodings may be classical or quantum, depending on what is the resource we want to consider. So when they have access to direct communication only, Alice and Bob have to choose a fixed encoding and decoding and stick to it throughout the task, while if they have local source of randomness or private coins, Alice can encode and choose encodings and randomize over it, while Bob can all do the same for the decoding strategies. While here the encodings or decoding might not be correlated. But when they have access to public coins, they can have access to all the encoding decoding tuples and find suitable convex combination of them to satisfy the task. So having access to direct communication and private and public coins, one might wonder what is the minimum communication required to accomplish this task. So There have been work that consider protocols that compute the function or relation, in our case, with zero error, while some works allow for a small amount of error as denoted by epsilon. And then they see what is the minimum communication required. In our work, we for CCR and later for S-CCR, we a strong communication complexity of relations. We stick to the setups shown here. That is a one-way communication is allowed from Alice to Bob, and M is the amount of communication here, and they have access to private coins. However, sharing public coins is not allowed. And while computing the relation, they have to do it without any error. So we see the zero error scenario only. And after discussing the communication complexity of relation, a natural variant comes up where we consider Bob's objective is to output in different iterations of the task the set of all correct answers for every tuple x and y as input. This we call the stronger version of communication complexity. And this task for functions reduces to a completely trivial one, as for every tuple x and y as input, there is only one correct answer. However, for relations, this might not be the case, so it still remains non-trivial. And for this this task we call strong communication complexity, and for this task one can define a payoff given a P of R, which is the minimum over all the conditional probability distribution B given xy is the input and B is the output, such that the triplet xyb belongs to the relation R. And this task of S-CCR can be thought of to be equivalent to relation reconstruction, where the idea is for a random reconstructor to guess the relation, and the reconstructor doesn't have any prior knowledge of the relation he has to guess. The only access he has is to the statistics consisting of the triplet xyb that is collected after all the iterations of the game. And to successfully accomplish the task, the reconstructor has to have all the triplets that belongs to the relation popping up in some iteration, as we have discussed earlier. Else, the relation is not reconstructed perfectly. So one thing to notice, however, is that for relation reconstruction, you need a non-zero payoff, while for S-CCR, the payoff matters. Okay, for communication complexity of relation, or a stronger version, what Alice and Bob before the game starts can do is to have a strategy, and any strategy for Alice and Bob will correspond to some conditional probability table. For CCR, what the strategy or the probability table says is that it should not have non-zero probability for triplets that do not belong to the relation in the zero error case. So this is the only requirement, and for the S-CCR case, however, this should hold. Along with it, there is an additional constraint that PB given XY is always positive for all the triplets XYB that belongs to the relation. So having these two probability tables in mind, I would refer to them when we consider our relation at some point as an example.
Hi, Sumit.
Yes, sure.
Just to guarantee that that I didn't get lost on this start, you're dealing with a communication scenario.
Yes.
In this communication scenario, you define a relation. So you're going to have certain inputs that will belong to Alice, to Bob.
Yes.
Yeah. Oh, yes. The communication is also one way, and then you're going to have the output that is given by Bob, B.
Yes.
And so X, Y, and B are going to define this relation.
Yes.
You don't define any problem to attack right now, right? So,
No.
for
This is
example,
the generic setup. Yeah.
okay. And then you started talking, you talk about a little bit of coins because you can have two cases. Could you explain a little bit that again?
Yes, sure. So when they have only access to communication, as I said before, they have some encodings. Alice encodes her input in M-bit message, and Bob then decodes the message along with her input and gives some output. However, and this encoding and decoding are fixed. However, if they have local sense source of randomness, they can have some probability distribution over some encodings, and Alice can choose in some round some encoding. Sorry, Alice can choose in some round some encoding strategy, and Bob can do the same for his decoding strategy. While if they have some correlations, they can know, okay, Alice has chosen encoding 1, then I will choose some ith encoding, and if Alice has chosen encoding 2, I will choose the second encoding or something like this. In a correlated way, they can do the encoding and decoding. So these are the use of private and public coin pops up out here.
Okay, and then you start talking about the payoff, and you said that for CCR, the payoff is always going to be 0. Is that it?
No, this is the conditional probability table. So imagine the rows imagine a table consisting of the X, Y, and B, where the entries are the probabilities, these probabilities. Since in CCR, we consider that there should be no error when calculating the relation. So for every triplet that do not belong to the relation, Bob's output means the probability should be 0, so that Bob does not give the output B, for which it does not, this triplet does not belong to the relation R.
Okay.
Because it's a 0 error scenario, as I showed here. We consider 0 error scenario. If they Bob chooses to give some B that is not such that the triplet doesn't belong to the relation, then they will be calculating the relation incorrectly.
Okay.
So this is the constraint on the strategy they can choose to win the task or perform the task.
All right.
And for S-CCR, they need to output, Bob needs to output all the correct answers for every triple XY over here. So the probability needs to be non-zero according to the strategy. Any strategy this year.
All right. All right. Thank you.
No problem. Okay.
Sorry. So in your setting, the relation is given and fixed. Is that right? In the beginning.
Sorry.
I mean, the relation is given for your problem.
Yes, I will come to the relation later on. I'm just talking now about the setup, and then the relation is basically based on some type of graphs. And when I I will talk about orthogonal representation and clique labeling to introduce the relation, and things will be clearer probably then.
Yeah, but you mentioned reconstruction, so I'm just curious. The relation is already known from the beginning, or is not?
Okay. So for Alice and Bob, the relation is known. For this random reconstructor, he is not aware of the relation.
He did not know. Okay.
Yeah. So he sees the triplet. If all the triplets exist that belong to the relation, then he will guess the relations correctly. If there is some triplets that is missing, then he won't be able to have the final relation reconstructed.
So the purpose is to guess the relation or not. It is not like this.
Yes.
Oh.
Yes.
Oh, okay. So the purpose is to reconstruct the relation.
Mm-hmm.
Okay. Okay. Thank you.
Okay. So now, as I mentioned, the relation we consider is based on graphs. So I will talk briefly about orthogonal representation of graph. And here we consider a graph consisting of vertices shown here. The set of vertices is V, and the set of edges they share is given by E. And a clique of a graph is a complete subgraph. For this graph G, what orthogonal representation does is assigns to the vertices of the graph some vectors in the vector space CD in such a way that if two vertices are adjacent, then the vectors that are associated with the vertices must be orthogonal. And there is another constant that if for two different vertices, the vectors assigned to these vertices should not be the same. Such a representation of the vertices is called orthogonal representation, and the orthogonal representation is said to be faithful if for any two vectors assigned to vertices, they are orthogonal if and only if the vertices are adjacent. So the vertices that are not like this won't have orthogonal vectors assigned because they don't share an edge. And the minimum dimension D in which the graph has some faithful orthogonal representation is called orthogonal range. And this minimum D is lower bounded by omega, which is the maximum clique size, and is upper bounded by the order of the graph. So this will come handy later. And now let's talk briefly about binary coloring. For a graph with n cliques, n maximal cliques, and the clique size omega, what binary coloring does is it assigns the vertices values 0 and 1 in such a way that if two vertices are adjacent, they are not simultaneously assigned the value 1. And there is a second constant that exactly one vertex in a maximal clique must be assigned 1. So while assigning binary colors to a clique of size omega, there can be different possibilities, omega to be specific, because each vertex can be 1 while the rest are assigned 0. So these omega binary colorings of a maximal clique corresponds to omega different label. So this is what we call clique label. And for say clique C2 in this graph, n is equal to 3, there are 3 maximal cliques and the size of the maximal clique is omega. For second clique C2, one can see the different binary colorings correspond to 3 different clique labels. And now that we have gone through, talked about clique labels, I will discuss what the problem we are considering, and the relation will be defined by this problem. So we consider orthogonality graph. By orthogonality graph, I mean a graph with n cliques and of maximal clique size, and the size of the maximal clique is omega. And for this graph, we have some orthogonal representation in minimum dimension. And the set of maximal clique is given by C, and omega is the set of all clique labels for a given clique. And Alice and Bob know a priori what the graph is, what the faithful orthogonal representation in minimum dimension is. So this is something of a common knowledge for both of them. So in this problem, Alice gets a input that is a maximal clique and a label of the clique. So X is C cross omega, and Bob gets as input some maximal clique CY. So Y here is also C. And at the end, Bob has to assign some clique label to his maximal clique. So the relation that happens to be considered here is RCLP, and it is specified by the constraints that Bob has to follow while assigning the label to his clique. And the constraint we call this consistent labeling of pairwise clique, and they are as follows. For the situation when Alice and Bob receive cliques, maximal cliques, CX and CY, and this maximal clique happen to share some vertices, then the binary coloring of these vertices that happens by Alice's input label should be same as the binary coloring of these vertices by Bob's output label. So, for instance, consider a graph here. If Alice's label colors this vertex as 1, then Bob's output label should also color this vertex as 1. And Alice and Bob may receive the same clique as well. However, if Alice and Bob receive two different maximal cliques, and the maximum cliques happen to have vertices that share some edge, then these vertices should not be simultaneously colored value 1. That is, the label should not color these two vertices 1 simultaneously. And in all other cases, Alice can choose some label independently of Bob's input. Sorry, Bob can choose a label independent of Alice's input. So this defines the relation RCLP will be considering. And for this distributed clique labeling problem, one can consider the communication complexity of relations as well as the stronger version of communication complexity of relation. In the communication complexity of relations, as we the CCR, as we talked before, the 4 tuple CX, the Alice's input maximal clique, the label for Alice, Bob's input maximal clique, and Bob's output label must belong to the relation. And in the case of S-CCR, Bob has to output all the labels that are that go for input clique CX, input label A, and input clique CY for Bob. So as stated before, he has to give all the correct answers for the triplet CXA and CY. So the conditional probabilities shown here must be positive. And as an example, consider this graph again with two cliques, two maximal cliques of size 3. We denoted by G23, and this is the relation. For this relation, the conditional probability table that Alice and Bob needs to have is of this form. The rows are labeled by CXA, clique 1, clique 2, and the coloring of the cliques the labeling of the cliques, and the columns are labeled by CY and the output label of Bob, because there are 3 output labels for each clique, and the zeros correspond to the fact that these labels are such that the triplet CXA and CY do not belong, CXA CYB do not belong to the relations. So they should be avoided at any cost. And the positions marked with star correspond to the, in the case of communication complexity, the regular communication complexity should be non-negative up to normalization, so that Alice and Bob accomplish the task. However, in S-CCR, these stars, this position marked with stars, should be positive up to normalization. So now let's talk about communication complexity of relations for the RCLP that we defined before, and the graph is consists of n cliques of maximal clique size omega, and the inputs and outputs are the same as before. For this, we saw that when the type of communication is classical, then log omega c bit is necessary and sufficient for accomplishing the task. And this is this can be seen directly if one replaces the position with stars by zeros and ones, and one will end up with omega independent rows. So they can be encoded in a omega level system and sent to Bob, and the Bob can give outputs that are correct. While in quantum case, this also this amount of communication is also necessary and sufficient. That is, Alice and Bob need to send Alice needs to send log omega qubits. So there is no quantum advantage for the relation. However, there will be something that is an advantage I will discuss for some class of graphs while considering strong communication complexity of relation. Sorry. So for the stronger version of the communication complexity, while considering RCLP, we will focus on graphs that satisfy 2 features. The first being every vertex belongs to some maximal clique. So, every vertex belongs to some maximal clique, and for 2 vertex that are in 2 different cliques, 2 different vertices that are in 2 different cliques, there is a third vertex that is adjacent to exactly one of them. For V prime, there is a U that is adjacent to either V prime or V, but not both. In short, we are avoiding a graph of this type, where the vertices shown here and here, the top and the bottom vertex have exactly same orthogonal relations, or share the edges with all the other vertices in similar manner. So we do not consider these kind of graphs. So for the graph that G and omega that satisfies Z0 and Z1 condition, we show that to achieve strong S-CCR, they have to communicate log cardinality of V C bits, where this is the order of the graph. So to see this, one can argue a bit and come to, means the argument is as such, if you try to fill the stars with non-negative with positive values, then one can see that there will be V number of rows that are distinct, and they have to be encoded in separate alphabets, message alphabets, and thus communication of the order of graph is necessary. Sorry. Okay, there is a problem. Well, okay, something I perhaps got deleted. Okay, so I'll just state it because it's not here. So for quantum communication, all right, for quantum communication, Alice and Bob needs to communicate log dr qubits, DOR. The DOR is the minimum dimension in which this graph has faithful orthogonal representation. And this DOR, as we talked before, is upper bounded by the order of the graph, while it is lower bounded by the size of the maximal clique omega. So in quantum case, they need to just communicate log DOR. And the quantum strategy in this case is something I will discuss now. And for this relation, say G and omega is the graph, say the one shown here. And what Alice does is on getting a maximal clique and label, the label corresponds to, say this is the maximal clique, and the label corresponds to some vertex which is assigned 1 by the, which assigns binary color 1 to the a vertex in the clique, say V2, and Alice sends the state corresponding to the vector assigned to vertex V2. And after sending the state, what Bob does is performs a measurement corresponding to her clique CY. Say this is the clique he receives C2, and the vertex have some vectors assigned to them, and the projectors are the correspond to these vectors. And when after performing this measurement, he receives some outcome, and the output label is exactly the corresponds to the outcome he receives. So while communicating a d-dimensional quantum system, the maximum payoff they can get is as follows. Say we consider some faithful orthogonal representation in dimension d, and we find the minimum overlap between any two vertices that are not adjacent, and take the minimum, and this minimum is maximized over all faithful orthogonal representation. So this is the maximum quantum payoff they get while communicating d-dimensional system. Okay, it was missing over the slide I discussed before. Okay, for S-CCR, again, having these two results for classical and quantum, one can consider a specific class of graph as an example, where all the graph consists of maximal clique of size omega, and all the n cliques, n maximum cliques are disconnected from one another. For such a graph, the DOR is the faithful orthogonal exists in minimum dimension omega, and since there is a faithful orthogonal representation in minimum dimension omega, the quantum communication required becomes log omega, while the classical communication, being the order of the graph, is log n omega. So the quantum communication is independent of the number of cliques, and one can increase the number of cliques, keeping the clique size same, and have unbounded separation between classical and quantum resource. However, it is to note that not only graph of this type give the advantage. There can be more general graphs that give unbounded separation. Now I'll talk about when the quantum advantage exists. So the quantum advantage for the task exists when the orthogonal representation for the graph is in dimension less than the order of graph. And we explicitly provide an example of such graph. The class of polygraphs helps show some quantum advantage, and these class of graph are these are a class of simple graphs that are undirected edges, and the vertices of this graph denote some element from a finite field, fq, where q is a power of prime, and q has the following form as well. It's 4k plus 1, where k is an integer. So q can be 5, 9, 13, and so on and so forth. And two vertices representing some elements of finite field share an edge only when their difference correspond to square of some other element in finite field. So these are the two polygraphs as an example shown here. And we argue that the class of polygraphs satisfy the property G0 and G1. And so we can consider the RCLP game as we discussed before. For this class of graph, the classical communication is again the order of graph, that is q, because there are q number of vertices in the graph. The classical communication is log q, and the quantum communication turns out to be log of q plus 1 by 2. And this is the dimension in which the graph has most optimal orthogonal representation, and the payoff turns out to be 2 over square root of q plus 1 whole square. So having showed the advantage for some general class of graphs, let's talk about the situation when they share public coin. Now they have some correlations which Alice and Bob can use as assistants for accomplishing the task. So in our game, when they share correlation, the quantum and classical advantage disappears, but one can consider a scenario where one can quantify the amount of shared randomness or public coins that is required to accomplish the task. So for this purpose, we consider a class of orthogonality graphs, G and omega, that satisfy the properties G0 and G1 as before. Also, they have faithful orthogonal representation in minimum dimension omega. So the DOR is omega. For this class of graph, we say, okay, some bounded amount of communication is allowed from Alice to Bob. That is log omega in classical and quantum case. And then what is this amount of shared randomness they need to accomplish the S-CCR of this relation, RCLP. So we show that for classical system communication, when the amount is bounded by log 2 omega, it requires this lambda amount of shared randomness at least, where this lambda for a graph G and omega, n is the number of maximum cliques and omega is the size of the maximum clique. And this lambda G and omega 2 is the amount of shared randomness that is required when the clique size is 2, maximum clique size is 2. So this lower bounds the amount of shared randomness required, and this amount is again greater than equal to log n, where n is the number of cliques. So the amount of shared randomness that is required while communicating a omega level system, classical system, grows with n, where n is the number of cliques. While in quantum case, when sharing omega qubits of communication, they do not have to share a priori any public coin. So one more thing to note is that this is the amount of shared randomness that classical communication needs. It may not be sufficient, but it is necessary. But this amount of shared randomness does not lead to maximum payoff. The payoff is the function that I talked about before. And in order to achieve the maximum payoff, they need more shared randomness. And this amount of the amount of shared randomness this need is connected to the existence of orthogonal arrays, which is an interesting field in itself. And they have some applications in quantum information where they have been shown to have some relations with absolutely maximally entangled state, multipartite entanglement, and error correcting codes. So if we have some time, I'll discuss about them in a brief manner later. Okay, so one of the interesting results that we saw is for graphs that consist of maximum clique size 2 and all the maximum cliques are separated, if one C-bit of classical communication is allowed from Alice to Bob, then they need to share public coins that if the public coin is classical, the amount grows as order of log n, where n is the size of the n is the number of maximal cliques. While if they share quantum public coin as a quantum resource, then they just need to share one EPR pair. And if they and they can achieve the S-CCR with non-zero payoff. So this now, as promised, I will talk a bit about some of the applications of our task. The first first application that I will be talking about detecting MUBs. Mutually unbiased bases have been very interesting in many different information theory tasks and have some, and their detection or certification is also quite important. So in our game, in the task we consider, if we have graphs with n maximally disconnected cliques, then for this task, if Alice and Bob communicate log omega qubits alone and not share any source of randomness, then if they receive some payoff that is maximum, in this case it is 1 over omega, then this certifies that Bob's measurement must be those corresponding to the MUBs. Next application is semi-device independent detection of non-classical resources. Here we consider again the S-CCR task with the direct communication alone. And for this, if Alice and Bob manage to get payoff that is positive while using communication of dimension of the order of graph equal to the order of graph or less than the order of graph, then the system they use must show non-classicality. And if the communication is promised to be quantum, one can and they receive non-zero payoff, then the dimension of the quantum system must be greater than DOR, where DOR is the faithful orthogonal range of the graph. So this is the application that for semi-device independent dimension witness. Now I'll draw some comparison with the works that exist in the literature. So the first four works, so exponential advantage, and the work by Burman et al. And Bar-Yosef consider partial functions, and in zero error, when they allow for protocols with zero error alone, they show this. Sorry, there is okay. Sorry, I was seeing the wrong. Okay, so they okay in the work by Burman et al. And they consider partial function and not allowing for public coins in zero error setting. They show exponential advantage, while Raz considers a relation and for non-zero error, considering protocols that allow for error and also allowing for public coins, they show some similar results. In case of Bar-Yosef, they consider relation and allow for non-zero error and public coins, but they show exponential gap. In the first and the third case, the size of the input is finite, while in the second case, the size of the input set is infinite. In a recent work by Gupta et al., they consider a finite size input based on partial function, and in the zero error setting, they allow for public coins and show some polynomial gap. The partial function they consider is inspired from is based on Cochin-Specker non-contextual graphs, that is the graphs that are not binary colorable. In our case, we consider graphs that may or may not be binary colorable, and it is irrelevant for our it is not required for as an assumption for our case. We consider we saw an unbounded advantage when considering zero error scenario with deterministic protocol, that is without any public coin assistance. So I'll conclude with some open questions. In the task we considered, we did not allow for public coins. So one might wonder, is there a variant of the task that allows for such advantage even when public coin is allowed? And here in this work, we also considered the zero error scenario. Then the question remains whether the advantage still exists when there is some error allowed. And we propose a scheme to detect MUVs and have some dimension weakness. But is this scheme robust to noise is something that needs to be seen. And as finally, the task we consider may have some similarities, or it's still to be explored with sampling complexity, where Alice and Bob had to output Alice and Bob do not have input, but they have to output something following a probability distribution. So this brings to the end of my talk, and thank you for your attention.
Well, thank you for your talk, Sumit. Now I'm going to open for further questions, if the audience has any.
Sorry, I have a question about the strong CCR.
Mm-hmm.
So wait, you said that
I think we
the
may
S-CCR. Sorry. So I'm just wondering your definition. I mean, you said that you must output all the possible results for S-CCR. So which means that if you are do the sampling, I mean, you have to do many measurements. So do you have to consider how many measurement is possible, or you just assume that it is possible to output all the outcome?
Okay. In here, while defining S-CCR, Bob has to give output all the correct answers, but then may not be necessarily in the same round. So if the task is done, means if they are asked, given different inputs in different iterations, and if one collects all the iterations, then Bob's output should cover the set of all B's such that for every tuple XY, it belongs to the relation. So in each round, they need to perform only one measurement. Means they may perform more than one, but only one is, it can be considered as a single measurement before Bob gives an output.
So you mean in each round you just need to output an outcome, but you must have many runs to have all the outcome comes. Okay.
Yes.
So in this case, is there any connection to the number of measurement you need to perform? Is there any kind of question related to this you can consider?
The way I see it, even if Bob performs more than one measurement, then because he has to give only one output, then the two measurements that Bob performs can be clubbed into one single measurement, or some the first measurement can be treated as a transformation, and or post-processing, so it's just one measurement, I would say. I don't think he will doing multiple measurement will give something interesting. I don't know.
Yeah, but my thinking is that even you run many, I do not mean for getting one outcome for several runs. I mean, if you want to have all the possible outcomes, but if there are some of them have very low probability, and even you run many runs, it's possible that you cannot get the outcome. So that's my thinking. Okay, anyway.
Sorry, I do not maybe understand and explicitly, but maybe I think what you want to say, because they have to give a correct answer in all the, but they do not have to give a correct answer, all the correct answers in a given run. So even if the probability is lower, Bob can choose to give only one output. So I don't know how it will help, but maybe it might be interesting to see.
Oh, okay. Thank you.
I think Pavel has a question or commentary.
Hello, everybody. I have a short commentary. Yes, it is right that if you really want to reconstruct, okay, if you interpret the game as a reconstruction, then of course you have to have at least one outcome for any star, and then obviously the number of the settings, the pair scales accordingly. Okay. However, if you consider it as a Bell inequality type, in quotation mark, because it's very far from that, right? But if you consider it as a game scenario, then it is enough to be sure, if you put a high payoff for being, you know, then it is just enough to say, okay, I should have a chance to pick up, for any setting, to pick up that particular one. So yes, there is a different perspective, but of course your question was right. Thank you very much.
Okay. Do we have more questions? Okay. Well, I'm just curious about some things, Sumit. For example, you talked very briefly about the function, like here in the slide. So you have a function, so we're going to have one correct answer in a relation where you have multiple correct answers. And you also talked at the end about partial functions. So how would exactly this scenario change if you're considering these functions, and what are these partial functions they're considering in their work?
So when considering functions instead of relations, there is for given xy, Bob has to compute some f of xy, and there cannot be two results that Bob can choose to give. So this is essentially what complexity of function would be. While in relations, there can be more than one correct b that goes with x and y. While in partial function, what happens is for some input x that Alice gets, there is a promise on the input that Bob will get. It's not fixed, but not fully random either. So for each x, there is a subset of y that is allowed from which Bob gets an input. That is a partial function.
Okay. So all right. I think I just got a little bit confused because you're defining this relation as the set of the variables that Alice and Bob have. So the inputs and the output. So like when you talked about the function, I would consider just the output that they're doing, because you're not like when a relation, you're trying to satisfy this x, y, and b. Okay. And I saw also that on your further questions, you didn't, at least I don't remember right now, you didn't mention trying to consider a two-way communication scenario.
Yes. So yes, we haven't considered a two-way scenario. We just have one way, and this is also Okay, this is also one of the open questions, whether one can have similar tasks with two-way communication. Maybe it will help with even when private coin is allowed. Means this is something that needs to be seen and we haven't considered in our work.
Pavel wants to say something.
Well, just I want to mention we did have considered that, but we didn't get to conclusion, right, Sumi?
Yes.
So there's nothing about it in the paper. Okay, thank you.
Okay, thank you. And perhaps lastly, if you could go a few slides back.
Sure, just
because you talked about getting an advantage, right? And then you say that if the DR is going to be less than the order of the graph, you can find some graphs for which you're going to get this disadvantage in the communication scenario. And then you gave one example of the Paley graphs. Are those the only ones that you found? There are some other, or there's some structure to them that is going to help us to see this advantage?
This is an interesting question. This class of graph is one. However, one can consider some extension of this disconnected cliques, where each two cliques, each two maximal cliques share at most the pair of any pair of maximal cliques share at most omega minus 2 vertices, or have omega minus 2 edges running from one to the other. So there can be n such cliques, and those graphs will also show quantum advantage, and the gap will scale as the order of the graph versus omega. However, we do not have a way of knowing when a graph will have means an orthogonal representation in less than V. Although it seems that for any graph, it has orthogonal representation in the order of graph. But if it is for some graph, if that satisfy the condition Z0, Z1, is it trivially satisfied DOR is less than V? This is something is open and could be seen. We haven't addressed this yet.
Okay, thank you. I saw that Hayato also had a question.
So can I ask a basic question?
Yes, please.
So you show the necessary and sufficient communication for such situation. So did you show the upper bound of the communication for a certain strategy or any strategy available in the general relation problem?
Okay. So here, yes, we showed that this is the upper bound because the number of rows, as I talked a bit before, in this probability table, say for a graph, the number of rows when you fill the entities with star has V distinct rows. So communicating communicating a V-level system would be sufficient, and Bob can use some randomized local randomness to output probabilities, randomize some over his strategies to give non-zero probabilities here.
Is it the classical upper bound?
Yes.
How about for quantum?
For quantum, they can achieve non-zero payoff with this DOR, and it is sufficient for non-zero payoff because they have a non. But in order to achieve the maximum payoff, what is the sufficient communication that is sort of open, because you need to have some optimal faithful representation, and this would correspond to the lowest theta problem. Means this will be connected to finding the most faithful orthogonal representation, and there are some upper bounds for this dimension, but the exact value for a graph is not known.
Okay, I see. Thank you.
Okay. We also had a question from Son. Is that right?
No, I just wanted to make a comment about that orthogonal representation being less than V. So like the class of graphs which will give quantum advantage, identifying. So as Sumit was saying, that identifying those set of graphs is as difficult as giving an upper bound to the orthogonal representation for those graphs. So it is connected to, it is as hard as finding orthogonal representation for an arbitrary graph. So the complexity of the problem is that. So it is not very easy, I would say, but it is, it is kind of intuitive to see that there will be lots of them, because it is only ruling out the case where the orthogonal representation is the order of the graph, like the V, the total number of vertices, which is kind of very special kind of graphs. So one can intuitively understand that there will be lots of graphs which will almost many graphs will give quantum advantage, but to actually identify the class of graphs like in a very closed form is not very easy, like giving finite number of conditions on the graph. Yes, so that is what I wanted to add.
I see. Okay, thank you.
It seems, sorry, just maybe a joking. It seems like this Kolmogorov complexity problem, right? That almost all sequences are compressible. They cannot know whether the given one is compressible.
I see. All right. I think we don't have any more questions. So let me thank you again for coming here and for giving us a nice talk. It's an interesting work. And let me stop the recording now.
Thank you.
Okay, thank you.
Thank you very much.